from which we will later obtain the specific heat, and it is defined as the amount of energy needed to raise the temperature of an object by 1 degree centigrade. And it works in the following equation. The heat equals the heat capacity times the difference in temperature. And of course this should be energy units of energy divided by units of temperature, which in this case we can use joules by degree centigrade. And from this we can obtain the specific heat. Specific heat is defined as the amount of energy needed to raise the temperature by 1 degree centigrade, to raise the temperature of 1 kilogram of a substance by 1 degree centigrade. So this one right here, as it is expressed in joules per degree centigrade, it is proper of each object. But this one here, it's a property of each substance. So we can obtain the specific heat as the heat capacity divided by the mass. And this we can substitute in this formula, and we would have that the heat equals the specific heat times the mass times the difference in temperature. So this is a very important value, as it can help us describe how much energy we would need to change the temperature of any object. So another important application of heat is calorimetry, and calorimetry is a technique used to measure thermal energy transfer, which is hard to measure directly, as we have a scale of how thermal energy is transferred, which is temperature, but it does not actually represent the units of heat. So when we use a calorimeter, what we have is normally an isolated system, just like this one. Very fancy calorimeters are normally made of some kind of metal and have some isolating substance in the middle, like a double cylinder. We normally, well, in some experiments we can fill it with water and place an object inside and see how temperature flows. So we normally use also a thermometer, a nicer thermometer, in order to measure the changes in temperature. And through that, using the formulas we just learned, we can measure the changes in heat, because we are isolating our system and maybe even our surroundings if we are, I don't know, surrounding an object with water or whatever we want to do. So through these objects we can measure a specific heat, but in different ways, in a constant pressure, in a constant volume, or in a molar way. So this is a very important technique for experimental physics in this area. So another important part in order to solve the problems that we will face throughout this chapter is latent heat and phase transitions. So latent heat is the specific amount of heat needed in order to go from one phase to another. So for example, we can have latent heat of fusion or of vaporization, and we can change this formula in order to solve for the heat from using the specific heat and the difference in temperature to just using the mass and the latent heat of whatever change of phase we're doing. And this will depend not only on the change of phase, for example, if we're going from liquid to solid or from liquid to gas, but also on each substance we're working with. And we can also note this for another two weirder phenomena, which are sublimation and the formation of plasma, which is like the next level after the formation of a gas. So this is also very useful for the problems we will be using, because for example, whenever we try to change a phase, if we have, I don't know, a liquid at room temperature, we have to first raise that liquid to 100 degrees. And then, once it is at 100 degrees, as we have seen in the graphs that show how temperature changes, there is a point in which both phases remain the same. Both phases are present. And in this point is when we need the latent heat, because through this change we are not actually raising the temperature, but we're using the heat energy placed in order to go from one phase to another. So that is a pretty important concept. Something else that is very important that we have to learn is the way energy, thermal energy can be transferred. So there are three main ways. We have conduction, convection, and radiation. So conduction takes place whenever we have, I don't know, certain material here, something that joins this material to another. Let's suppose this one is at 100 degrees centigrade, and this one is at 0 degrees centigrade. So whenever heat goes from here to here, because it of course will flow in this direction, this is a type of conduction. So we, for example, can experience this whenever we are in the lab. If we heat, I don't know, a metal spoon, well, the heat is concentrated in the part that is directly in touch with the fire, and it will transfer to the longer part of the spoon through your hand. So this is a type of conduction. And for this, we have the following formula to calculate the power of conduction, which is the thermal conductivity of each material, which is represented by K, times the area, times the difference in temperature, which will be the one from the hotter one minus the colder one, divided by the thickness of the material. The length of the material. So in this case, we can also change this and use L over K as a constant R. This value of this value of R is also known as thermal resistance, and it is represented as L over K. So we can have this formula as the area times the difference in temperature divided by R. And this is a specific of each object because it depends on the thermal conductivity and the length of the object. So, besides that, we can also have a form called convection. I'm going to erase this part here so we can understand it better. So, convection is mainly the principle behind, for example, air conditioning. So, what happens in convection is that the heated air tends to go above. So whenever that heat goes to the upper part, I don't know, of this room, for example, the colder one will go below. For example, in an air conditioning system, as we heat, as we're trying to make the room colder, the heat will leave the room by going above, and the colder air will stay where we are. So for this, we can also know, for example, the ocean currents and the heat that enters the atmosphere through the sun work also through convection. And the next way we can transfer energy is through thermal energy, is through radiation. We already know objects tend to radiate this type of energy, like they release it to the environment, and some objects are better than others at doing this. So, in this case, we also have a formula to calculate the power of radiation, which equals this letter here, which is Boltzmann constant, times E, which is called as emissivity, which is how good an object is to radiate heat, and it normally goes from 0 to 1. Although there is no object in the universe that has any of these values. 0 would be something that does not radiate at all, and 1 would be like the perfect radiating object. So we normally have values between these both levels, times the area, times the temperature to the fourth power. So these are the different ways we have of transferring heat, and all of them can help us solve different problems. So we have also some applications for this chapter. for example, global warming that can be explained, as I said before, by the convection that takes place in the atmosphere. We can also take, for example, heating in computers. They normally have a cooling system that goes active whenever the heat is like too much for the computer to stand it, and it can actually break down because of it. And we also can have geothermal energy, which is the energy we obtain from the heat that comes from the center of the earth, which is actually pretty hot. So these are some applications that are pretty important and actually relevant in everyday life for these topics that we just learned. And that's all. Thank you.